Today, hi guys, because we want to start vector fields. That's kind of the summit of the course. Everything we did, in a way, is to understand vector fields. Not completely, but most of the things we are doing, well, can be applied to vector fields. So this is chapter 6. So last chapter, by the way, vector fields. I think this is 6.1. So what we did when we discussed vectors, it was just about one vector. We discussed vector algebra, right? I mean, so the idea of vectors, of course, you know, from many sources. I mean, and then vector algebra. So what was the vector algebra? So when we discussed the, sorry? No, nothing. When we discuss vector algebra, we discuss addition, scalar multiplication, and then cross product, dot product, differentiation of vectors, things like that. So addition, scalar multiplication. Dot and cross products. Etc. So this is all we did in previous, maybe actually early chapters. So today, this vector field is different. So this is all old stuff. So today we are going to look at this stuff. So what is a vector field? So vector field, we can think about it like this, is an assignment of a vector to each point of your space. At each point of your space, so imagine you're like space of this blackboard is a 2D space. At each point, you assign a vector. In any which way you want. There is no one who can tell you this is better than that or so on. So you can just assign vectors in any way you want, right? And then you say that you have a vector field in that region, okay? So what it takes to define a vector field then is like this. For each point in your space, like x and y, right? Belonging to this domain D, which is, by domain, we mean just a subset of R2, right? For each x and y belonging to this domain, a vector f of x and y is defined. But this f of x and y obviously has two components, right? Has an I component and a j component, or a first component and second component. No matter how you want to think about it, so I just write it like this: a of x and y, I, plus b of x and y, j. You can write it like this, but of course, vectors, you can write it as components also. A of x and y, b of x and y. And sometimes you want to be a bit cool and don't mention even those x and y. That's kind of childish to write x and y all the time. So we just say, we are adults, we understand what's going on, we just write a and b. And that's really cool. That's a good notation. That's kind of slick, nice notation. Because you don't want to write all these messy things. It's better to use imagination and know what is behind the scenes. Anyhow, so these are different ways of talking about the same object, which is a vector field in the plane, right? So this is a vector field in the plane. Vector field. To be more precise, actually in the domain D is defined, right? It's just in the domain. In a domain. But there is nothing to stop you working in domains in 2 dimensions. You can work on in domains in 3 dimensions. Right? You can go on 4 dimensions, 5 dimensions, 1 dimension. It's completely free. You're free. So I just write here that you can do the same in any dimensions. Okay, same definition works in any dimension. So basically, then we just say, okay, a vector field in 3D-dimensional space. So this is like your x, y, z coordinate, and you're in 3D. Then you have assignment of vector at each point. I mean, at some points the vector may be 0. It's completely fine. You can just define at some point you want maybe this function, both of them are going to be 0, but that's fine. Well, I mean, as a matter of fact, your vector field can be 0 everywhere, and that's totally fine. There's nothing to stop you by defining it in that case like that. Okay, so in this case, we just say f of x, y, z would be a of x, y, z, I plus b of x, y, z, j plus c of x, y, z, k. So you see, to define a vector field in 3-dimensional space, you have to define 3 functions, each of them of 3 variables, right? So you notice that the vector field is quite a complicated object compared to functions, right? For functions, we just have one function, a of x, y, z, or a of x, y, z, t. So, but for vector fields, we have 3 functions here. Only if you know these 3 functions, you have to define your vector field. So you have to really pay due respect to vector fields, because these are more complicated objects. Here also, it's not just one function, there are 2 functions, right? So that's a general, so again, like over there, you can just write it as A, B, C. Now you might complain that, hey, this is like a vector, but again, as we discussed, you can imagine A, B, C are themselves functions of x, y, z. Then this is really a vector field. So. Or you can also write it as AI plus BJ plus CK, right? So that's what we do. Okay, so that's very good. Now, what we have to do first is to discuss some examples of vector fields so that we know we have some facility with vector fields first. We have to develop that kind of kinship with vector fields first. So the best thing to do then is to look at examples of vector fields that kind of appears naturally in many places, and then look at this. Okay. So now, but before giving example, so let me give you some examples from nature. Examples of vector fields in nature. Okay, so let me look at first example. For example, you may be, in some case, interested in studying of fluid flow, for example. Fluid flow. So by fluid flow, I mean, e.g., for example, river, e.g., water in a river, e.g., water flow. In a river. Okay, so this is like, so let's assume the river is just two-dimensional for us. We don't think of the depth of the river, just the surface, or very, very shallow river, we can think. So imagine this is. So in this case, the field that defines this fluid flow for us is the velocity field of this water here. So at each point, so now we just think of one point here, and we look at the flow, the velocity of the water flow at that point and at a given moment of time, right? So at this point, you have a vector. You can have vectors. Or you can have, maybe there is some obstacle here, for example, there's some island in the river. And then, of course, this is not passing through this, so it has to kind of be observant of this island here. So you just cannot, so maybe there's another island here. And then it kind of maybe passes fast here and slower here. So in this case, F is just the velocity field. So F is velocity vector field. But then there are two things. I mean, one thing is that at a given moment of time, right? Because when time changes, of course, the velocity profile could change because at one moment, maybe there is some more water coming in and there's variations of the river flow and this thing. So we are just thinking of one moment of time, at a moment of time. So at a fixed moment of time. So this is then is usually denoted by V. We can just say this is equal to A of xy I plus D of xy. Okay, so this is the velocity at each point. You see it has different amount, different directions, but you can sense that in general it's going to be like that. But some places there may be some vortices. So I mean, water may even go around at some places. So there may be some vortices developed some places. So we will talk about those vortices later on. This is kind of interesting phenomenon. We'll discuss it later. So that's one example. So any questions? Okay, so second example is these vector fields that you study in physics. For example, the field due to gravitation of some object, gravitational vector fields, or magnetic vector field, or electric vector fields. These are three great examples of vector fields that you should always have in mind. So the gravitational field, So what is the gravitational field? Of course, Newton's law. You know, this is Newton's law. It says that the force of attraction between masses is equal to G times M1 and 2 over R2, right? So this is Newton's law of gravity. G is a constant, M1 and M2 are masses, and R is the distance between these two masses, right? So this is like here. And in the simplest case, if it's just a mass m1 here and mass m2 here, then this is distance r. But there is something missing in this formula. What is missing in my formula? It's a nice formula. It's good to remember it like that. But there is something missing there, right? What is it? Direction. The direction, exactly. This really gives the magnitude of gravitational force between attracting bodies, masses, right? This doesn't tell us what is the vector itself, but we know that this, there's an attraction, there's a pull here, so this is like F, and this guy is also pulling that, like this one. The amount, though, is always given by, so the magnitude is always given by that. Okay, with that in mind, now let us look at a specific example where you have a mass at the center. So a big mass like Sun is at the center, and Earth, like a small mass, is some distance away. Then so we are assuming that this is not moving, and this is just at the center, and is attracting, pulling this mass M towards the center. So we are interested in finding this vector as a vector field, which fills the whole space. Okay, so this is our task, find F as a vector field in this example. Okay, so what is F as a vector field? Well, we know that the magnitude is given by this formula, and M1 and M2 are little m cap m, and G is a constant. All we have to do is we have to find this vector. So what we have to do, we have to find the unit vector which passes through this M. This point is a given point, say, which is sitting at, M is not the point, M is the mass, sorry. Which is sitting at the point x, y, z, and is pulling towards the center. Okay, so then that R hat be the unit vector. My notation now is like this, so let R hat put the unit vector along R. So this is, and directing towards the origin. Towards the origin. Okay, if we just wanted to know this vector itself, which is sitting at the point x, y, z, what would that vector be? That vector would be x, y, z, right? Because this is just M has coordinates x, y, z. M is the mass, but its coordinate is x, y, z, sitting at x, y, z, right? Okay, but we have to normalize this, normalize it. So we have to divide this by 1 over square root of x2 plus y2 plus z2, right? And then times x, y, z itself. So this is all good, except there is one problem with this, and the problem is that this is directing in the opposite direction. So we have to change its direction by multiplying by -1. So then we multiply by -1, we get -1 over root x2 plus y2 plus z2, and then times x, y, z. Okay, and this is R hat, which is unit vector, which is pointing towards the origin, right? Pointing to this point M. But what we are interested in is not this vector R hat. We are interested in gravitational force between M and that point. And gravitational force is equal to 1 over R2 times R hat. So the force then is equal to, so let me write it here. I can erase my ruler now. So this is F is equal to 1 over R2. So let me write G M cap M 1 over R2, and here is R hat, right? Okay, so what we have to do is sum in, you get G M M, and that R hat is, we got it, so that's equal to 1 over x2 plus y2 plus z2 times 1 over square root of x2, y2, z2 times here, and there's minus x, y, z. So what do we get at the end? This is equal to negative g m m over x2 plus y2 plus z2 to the power 3 over 2 times okay, the distance is square root. I squared it. Okay, that's good. Times x1. That's my vector field F. So this is the gravitational field. Field of a mass m at O on a mass m, little m, at x, y, z. Okay, now there is something here we have to pay attention to. What is it that we have to pay attention to in this example?
The distance can't be 0.
The distance cannot be 0, that's right. So in other words, this vector field is defined everywhere except at the origin. At the origin, in fact, this vector field is, what is it? It's like infinite, right? It really grows. As you approach this point mass, the size of the attraction, the amount of attraction goes beyond limit. This is what theory says. I mean, this is a hypothetical situation. I mean, in practice, it doesn't happen because we cannot reach distance 0 in nature, and in that case, none of this stuff would work. You have to bring in totally different considerations, and that never happens in practice. But in theory, we have to stipulate that, in fact, this is not defined at 0, 0. So let me just write it like this. At the origin. So that's just one simple vector field that's defined by a point mass at the origin. So now you can imagine if you have a distribution of mass. So here is example 3. The vector field due to attraction of a distribution of mass in space. Then you immediately get into very, very complicated situations if you want to consider this sort of situation. So let me give you an example. Here is an example. So imagine you have, again, we are in 3D space. Imagine there is some distribution of mass like this. So there is a kind of comet or a rock, space rock, which is like this, and there is another one which is like that. So we could have very complicated geometry, right? And then at each point, you can actually go on and define a vector field F. I won't write it because it involves some integration, but that's okay. So, but you sense that to a mass m at this sitting at any point in the space away from these bodies, the two bodies that are attracted, there's going to be some gravitational force. And finding this force is a very complicated task, right? So because we just, all we can say is that if you get near to this, the force is going to be mostly pulling towards this. Because the pull of this is going to be, so this is kind of lighter and away, so the pull of this is going to be negligible if you're close enough to this one, far away from this. But then somehow in between things changes. And when you get close to this, I mean, anything can happen. So there's going to be a very complicated profile of vectors, vector field in the space, which is going to be distributed like that. So easily, you can easily produce some vector fields which are very, very complicated. There is a picture in your book actually, which is nice. I liked it. Check the picture. I think even the first page in that chapter, there is a vector field of this situation, which is nice. So that's as far as the gravitational force and the vector field is concerned. But you have also, I mean, so here is another example. Perhaps the most prominent vector fields that you study in physics are electric and magnetic fields, right? EM fields. So EM fields, electromagnetic fields. Are there any questions? No. Electromagnetic fields. So the notation, there are different systems of notation, but the one that's kind of more in use, and I like it, is E and B. So sometimes it's called E and B fields or E. So E. So again, I am discarding the question of time totally. So I'm looking at vector field at a given time. If you want to be cognizant of the issue of time, you have to make it a function of time as well. But we're not talking about time now. So at the moment, we are looking at the electric and magnetic field as field space, like here. It's amazing amount of electric magnetic field going around, very, very complicated. And we kind of swim through this vector field. So let's call A of X, Y, Z. Again, there is secretly some T here, but we just don't think about it. It's a function of time as well. So usually this notation is EXI plus EYJ plus EZK. Now notice that this is a different notation now, okay? So it's a new notation that's also in use. And in particular, E sub X, EY, EZ doesn't mean partial derivatives. That just means the X component, the Y component, the Z component. Okay, so so warning is, be careful, is that EX is not partial derivative of E. Okay, so we know that electricity, distribution of charges in space produces electric field. And this electric field, the notation E is given by that. So, same for magnetic field. This time the notation is B of x, y, z. And again, t, we forget about t because we fix the time. We look at this at one moment of time. So that's again equal to bxi plus byj plus bzk. Okay, so that's good. So these are examples of vector fields in nature that I wanted to discuss. Then we'll go back to mathematics and we'll see what math can teach us about vector fields beyond what nature gives us or poses as problems. Any questions? No? Okay. So then back to math. Mathematics of vector fields. Okay, again, it's a good idea to think of some special classes of vector fields that, I mean, have those types in mind. Like the first example that I gave, a vector field pointing towards the origin, gravitational field of a mass, point mass at the origin. This is a very useful, very, very important example. So I'm going to give a few more examples of vector fields that we have to know in order to kind of develop some feeling for vector fields. So more examples then. One example that's kind of easy is constant vector field. Constant vector field. Well, I mean, the name suggests what it is. It's just constant. There is no x, y, z dependence, right? So f is equal to, say, a I plus bj plus c k. Well, a, b, c now are not functions of x, y, z. They are just constant. A, b, c constants. So if you draw this vector field, it's very easy to draw this vector field now. You just at each point you pick this vector ABC, and then everywhere else is parallel to that, and exactly the same amount. So that's a very simple picture of this vector field, the constant vector field, which is like this. So this goes on and on and on. It fills the space, same direction, same magnitude. I'm not very successful giving the idea of same magnitude, unfortunately. And it fills the space. So this is a bit like a river that's kind of flowing without any sort of distortion. So it's a kind of very, very boring kind of river. It's straight lines, and banks are straight lines, and there are no islands, there are no sources, sinks inside, no boats, no swimmers, no stones is thrown, huh?
No friction.
No friction, yeah, even more, yeah, that's right. So it's just going very, very smoothly, slowly in one direction, and it's parallel to itself. So that's good to have this in mind. Let me give you another example. These are kind of rotational vector fields. So what is it? So let me give an example of this. So imagine we have something like f of x and y is equal to, say, minus y over x2 plus y2 I plus x over x2 plus y2 J. Let's look at that, right? So what is this vector field? Can you draw this? Let us draw it. How does it look like? Well, this, we know it's a two-dimensional vector field. That's fine. But how does it look like otherwise? One thing you should notice is that this vector is always orthogonal to the position vector R, the vector that gives you the point of this. So notice that F is always orthogonal to R. Remember, R is this vector X and Y. Why is that? Well, let's take the dot product. F dot R is equal to, well, if you take the dot product, you get minus Yx over X2 plus Y2 plus XY over X2 plus Y2. This is 0. So that's a valuable information. It just tells us that at each point, like which is this direction or this position vector R, this coordinate XY. Now, your field is orthogonal to this, to the position vector R, right? Now the question is, does it go this direction or that direction, and by what amount? We have to decide. Does it go this direction or this direction? Which direction it goes? Going down? Yeah. Okay. You look very convinced. That's very good. Any other answers? Class? Which direction is it? Yes.
Does it have to do with like in the equation, the like x component is negative and the y component is positive, so it's the other way?
It's the other direction. Yeah. You see, if you look at it, imagine you are here, and then x and y are positive, but for f, the first component is negative. So it means that this x direction of f is pointing in this direction, and the second component is positive. So this is definitely going to be this. And the value of this vector field, the amount, if you are on a fixed circle, is just constant. Right? I mean, I'm saying absolute value of f, norm of f, is equal to square root of x2 over x2 plus y2 squared plus y2 again over x2 plus y2 squared. Right? So this is, we're just squaring the two things to find the norm or length, magnitude. That's equal to, well, I mean, this is like 1 over x2 plus y2. I just factor it out. Times square root of x2 plus y2. In any case, this is equal to 1 over square root of x2 plus y2. So that's 1 over magnitude of r, which is the position vector. Aha. So if you are at a fixed distance to the origin, the amount, the value of the field doesn't change. The magnitude of the field doesn't change. The field itself is changing. I mean, of course, here it's just. Okay. So it's constant, the magnitude is constant on each circle. Okay, so we have a very good picture. Now, what happens is that as you approach the origin, the amount of this field increases. It just gets bigger and bigger as you approach the origin. So for example, if you are at a circle, on a circle rather, which is half the distance to the origin, then your field is going to be like this. Much bigger. And as you approach this, so you get even much bigger. So it seems there is some vertex or vortex at the origin that really violently turns this around. And as you're approaching the origin, the amount of rotation just gets beyond imagination. It gets bigger and bigger. So that's a kind of, so this is an example of a vortex or rotational vector. So this is a vortex. You can have different type of vortices. I mean, this is not a very technical term I'm using now. You can have vortices where the amount of magnitude is constant. In that case, I have to take 1 over square root of x2 plus y2. Any questions?
I'm just thinking of the physical interpretation of this if it's a vortex per se. So at the origin, we would technically have, it would blow up to infinity. But in real life, I would think at the origin, you just have one particle that doesn't spin.
That doesn't spin, yeah.
Yeah. How does that?
So this is my kind of vortex. It's not nature's vortex. That's why I said that there are different types. I just use it as an example of a rotational thing. But we can have example where actually it doesn't change. The amount of rotation is fixed. And for that, so now that you asked, it was a very good point you raised. So let me now actually give you another example. So like f1 of xy, that would be like minus y over square root of x2 plus y2. That's a possibility. I can do that. Of course, mathematically, you can do it more or less anything except stupid. Okay. And notice that the length of this vector is what? Well, you get 1, no matter what. X and y. Right? So you get 1 for all x and y. So it doesn't matter how close you are to the center. It's always, there's a rotation which is fixed. So this may be more realistic, but in a situation where you want to show that actually it's going to 0, you can have, or so let me just give you another example which is close to yours. So that's something like minus yi plus x2. That really vanishes at the origin. Your vertex is really has no rotation at the origin, but it's exactly like going around the circle.
And is it constant up until the origin?
It's not constant. But the value on the circles are constant. Because it's, again, square root of x2 plus y2, which is a constant, depending on the radius of the circle only, not on where you are on the circle. But as circle shrinks, the value changes. Good point, yeah. Okay, so this is so we looked at basically 3 examples of kind of rotational vector fields that sort of convey the idea of vorticity at that point. So there's a kind of there's a sink or source could be, I would say. Now again, I'm not using these terms in a technical sense. I'm just using it right now as intuitive terms. We'll define it technically more carefully later on. Okay, good questions. Okay, any other comments or questions? Okay. Okay. Nothing. So now, one class of vector fields which is very important and we have to develop a kind of good understanding of them are gradient vectors. So now we are looking at some general theory again. So this is kind of gradient vector field. Gradient fields, vector fields. So what is a gradient vector field? So the idea is this. Of course, if you have a function f, little f, you can take its gradient and immediately gives you a vector field. So that's a very easy way of generating vector fields, right? So for any f equal to f of x, y, z, a function, you can immediately and almost cheaply produce a vector field without any effort. You get a vector field f, which is gradient of little f. We also write it as grad f. What is it? This is a vector field. This is like this. This is like df dx I plus df dy j plus df dz. Okay. Now, another notation is, of course, this is fxi plus fyj plus fz. Okay. Now, here, f sub x, f sub y, f sub z do mean partial derivatives. Okay, so in this case, we mean partial derivatives. Now, so this is the vector field, and this is called the gradient vector field. And a vector field is called gradient if it can be written like that. So that's a very simple definition. So definition, a vector field is called the gradient field. It's called gradient field if there exists a vector field f, capital F. Why did I write two fields? A vector field F is called a gradient field if there exists a function f, a function little f, such that gradient of f is equal to capital F, as we discussed. Now, this f is called the potential for f. Okay? So this f is called a potential. Now we work with this concept. So a potential for f. So that's a very important concept of potential of a vector field. Now the question that once someone introduces a concept like that is the following. Is it true that all vector fields, or for example, could it be, let me formulate it like this. Could it be that all vector fields are gradient fields? So is it that every vector field has a potential? So that is it true that any vector field can be written like this? You're shaking your head, meaning no. You're meaning no. Any yeses? Any yeas? Could it be that?
The partial derivatives need to exist.
Yeah,
for this to be
assume all partial derivatives exist. Assume those considerations are taken care of.
Well, then yes.
But then the answer is yes. Your answer then would be yes. Yeah? Answer would. You're shaking again. No. Why?
I don't know.
Yeah, no, that's great. No, it says that they should. In fact, the answer is no. In fact, we will see that the variety of vector fields that are going to be gradient fields is very, very limited. These are a very, very particular class of vector fields. And the first thing we have to understand is what kind of shape these vector fields have. Do we understand these vector fields at all or not? What is the profile of such vector fields? How do they look like? We have to understand that first. And we have to understand this question of when a vector field then has a potential or so. Okay, in this case, this vector field is also called a conservative vector field. It is, in this case, F is called a conservative. It's not a radical. Well, there's no such thing as radical vector field. In this case, thank goodness. In this case, F is called a conservative vector. So the notation is kind of abandoned. I mean, terminology is very abandoned here. We are just saying conservative is the same as gradient. So conservative field is the same as gradient field is the same as having potential. Well, I mean, let me give you an example. Of course, examples are very cheap to construct one way, right? If I give you a function, then you can just give digits. So let me give you an example so that you know what we're talking about. I'm going to finish in 1 minute. So, example, let f of x, y, z equal to x2, y2, z2. Then what is gradient of that? Well, this is the vector field 2x to y to z, right? 2x to y to z. How does it look like? Well, it looks like this. It's like kind of coming out of this like source. It's as though there is a source here and kind of pumps water out, right? And but okay, I mean, but as you go further away, the amount of vector field increases. So I don't know if this water analogy is very good here or not, but you can imagine as you go, you know, away from the origin, the distance from origin, the amount of field increases. I mean, the magnitude increases. But otherwise, it's kind of very nice symmetric vector field on this circle, on these spheres is constant. And the field is orthogonal to the sphere. So this is an example of a conservative vector field. So next lecture is going to be to define another type of vector fields, which are irrotational vector field or incompressible type of vector fields. And with those two concepts, there are two other concepts, divergence and curl, that come into the game. And the whole thing revolves around the interplay between divergence and curl and what they mean and how can we define also those operations in terms of integration. So we'll see. Okay, guys, thank you and have a good day. I'll see you on Wednesday. Okay. Yeah.
As is derivative, but it's not.
No, derivatives is not an issue. Existence of derivatives is not. What's that?
So you just said that not every derivatives is a burden to.
Oh, you mean should I? You want me to give an example of a vector field which is doesn't have a potential or is not gradient field?
Yeah, but the derivative
should exist. Yeah. Okay, so I'm going to bet, that's a good question. I'm going to bet with you. I write a vector field at random, and this is not going to be great.
Yeah,
So-
but it's random, so how is
What?
So we said there.
No, you're fixed. So let me first of all, let me just shut this spot.